let's start with a brief summary of the past few lessons. We'll let G be a group under multiplication and H its subgroup. And we've been working with cosets of H. So in particular, if we have a pair of cosets AH and BH, we can multiply them. And their product, AH times BH, by definition requires a fairly tedious calculation, but we've also found a shortcut for it. This product equals the coset ABH, so the shortcut tells us we can just multiply the coset representatives. Now, the coset multiplication shortcut doesn't always hold, but we've learned that if the shortcut holds, then G mod H satisfies the group properties and hence it is a quotient group. But the question remains, under what condition does the coset multiplication shortcut hold? And filling in that missing piece is the goal of today's lesson. Again, our lesson goal today is to find the condition under which the coset multiplication shortcut holds. But first, let's dig a little deeper into what it takes to show this equality, what it takes to actually prove the coset multiplication shortcut. Now, in this equality, both sides of the equation are sets. So let's first look at the left-hand side, AH times BH. An element in this set looks like alpha times beta, where alpha is an element of the coset AH, and beta is an element of the coset BH. How about on the right-hand side? Well, this is a coset ABH, so an element in that coset looks like AB times H for some element H in the subgroup capital H. Now, to prove the set equality, which is needed for coset multiplication shortcut, we have to show both inclusions. So first we need to show that the coset ABH is a subset of AH times BH. And we've already seen that this is always true. But it's the other inclusion that's a little more tricky. AH times BH is a subset of ABH. This is sometimes true, but the question is when. And that's a big goal of today's lesson. When does this second inclusion hold? Now please pause the video and work on day 24 classwork. And afterwards, we'll go over some of the problems and concepts. Let's first talk about problem 4, where our group was D4. And then we looked at the subgroup K, which contained the 4 rotations. So R0, otherwise known as epsilon, R90, R180, R270. And then we looked at the left and right cosets using the same coset representative, namely V. So the left coset VK, we took each element of K and multiplied them on the left by V, and we ended up with V, D prime, H, and D. And the right coset KV, once again, take each element of K and multiply them on the right by V, and we got V, D, H, and D prime. So what we notice is that the left and right cosets, VK and KV, are equal. They have the same 4 elements. And in fact, this is true regardless of the coset representative you choose. So we do have AK equals KA for all elements A in D4. But this is a set equality and not an element by element equality. In other words, the left and right cosets being equal does not imply that V times little k equals K times little v for all little k in the subgroup K. For example, V times R90 is equal to D prime, but that doesn't equal R90 times V, because R90 times V is just D. Instead, V times R90, which is D prime, and here's D prime in the right coset, so that's equal to R270 times V. And so once again, set equality does not necessarily imply element by element equality. So instead of saying Vk equals Kv for each element little k, what we have to say instead is that Vk equals Jv for some element j in the subgroup K. That's the best we can say. So for example, we've seen that V times R90 doesn't equal R90 times V, but it's equal to another element in K times V. In this case, that other element is R270. We now introduce a definition. Let H be a subgroup of a group G, then H is called a normal subgroup of G if GH equals HG for all coset representatives little g. In other words, in a normal subgroup, all left and right cosets of H are equal. And another remark is that we often say H is normal in G, and that means the same thing as saying H is a normal subgroup of G. Now, we've already seen an example of a normal subgroup today. The subgroup K in problem 4 is a normal subgroup of D4 because AK equals KA for all coset representatives A. Now, why should we care about normal subgroups? Because that's the missing link. H being a normal subgroup is the condition needed so that the coset multiplication shortcut holds in G mod H. And so we finally have our complete picture. If H is a normal subgroup, then the coset multiplication shortcut holds in G mod H. And then if that's true, we have a quotient group. G mod H is a quotient group. So in the next slide, we'll justify why this is the condition needed for the coset multiplication shortcut to hold. Here's our theorem. If H is normal in G, then AH times BH is equal to ABH. In other words, the coset multiplication shortcut holds. Now we have to prove a set equality, which means we have to show both set inclusions. However, one of them, namely ABH is a subset of AH times BH, is always true. And we showed that in day 21. So let's put a check mark next to this one, and therefore our focus will be on this first set inclusion. Here's the proof of the first set inclusion. We'll begin by assuming the hypothesis, namely that H is normal in G. Now, in order to show this set inclusion, we need to start with an element of AH times BH and show that that element is an ABH. So let's go ahead and do that. We'll let X be an element of AH times BH, so that it looks like A times little h times B times K for some elements little h and k in the subgroup H. And then at the very bottom, we'll jump to our ending. Namely, we'll show that X is an element of ABH, and that gives us the desired set inclusion. Now, we know what X already looks like. And we also know what we wanted it to look like. So let's take a peek at the second to last step to see how we can make that happen. So X is equal to AH times BK. And let's jump ahead. Ultimately, we wanted it to be an element of the coset ABH, and therefore, eventually it has to look like AB times some element of H. Now going back, we have AH times BK. Let's group the middle two elements together. So we have AHBK. We wish to flip this element HB, and that's where H being a normal subgroup plays a role. Now, since H is a normal subgroup, we know that left and right cosets are always equal. In particular, we have the right coset HB is equal to the left coset BH. And therefore, we don't necessarily have element by element equality, but we can say that an element in the right coset, little hb, is equal to some element in the left coset, namely b times j, where j is an element of the subgroup H. And now we can complete our proof. So this HB here can be replaced by b times j, and now we can regroup again and say this is equal to AB times JK, where J and K are both elements of H, and since H is a subgroup, hence closed, JK is an element of H. So this whole thing is an element of the coset ABH, and thus we can say that X is an element of ABH, and therefore that's the end of our proof. And this is just a reminder to please read about the normal subgroup test in chapter 24, since we didn't get a chance to cover it in class. And that's the end of today's lesson, and I will see you next time.